Welcome, everyone, to the May OWASP Austin chapter meeting. And today, our meeting is sponsored, the food is sponsored by our chapter revenue for memberships as well as our LASCON conference. And facilities are provided by National Instruments. Chapter leadership. I'm Tiana Chandler, the chapter leader. And we have some others listed here. I believe we have a few. Josh is here. I know Kyle and Bankham. And if you have any questions about the chapter itself, you can just come talk to any one of us. CPEs, if you would like to get a certificate it's eligible for an hour, CPE hour, just email me and I can get you a certificate. To show support for OWASP and our chapter, there's memberships available for individual members and for corporate members, as well as, and then there's actually student memberships available as well. And you can find out more information about memberships on the austin.owasp.org. Also, if you're interested in volunteering to help out, we have different opportunities. Again, you can talk to any one of us on the chapter leadership. We have a study group that's ongoing, and currently we're doing the Black Hat Python book, which is also here at National Instruments in Building A. It's during the lunch hour every Thursday. Matt Pardo is our education coordinator, and he can provide more information if you have any questions about that. And as far as conferences go, LASCON 2017 is going to be this October. And right now we have early bird registration through June 1st, which is tomorrow. So if you'd like to get that discount, you might want to go and register now. And if you're interested in presenting at the conference, our CFP site is up and submissions are accepted until July 1st. Bankham, if you'd like to add anything else to that. Oh, okay. Okay, maybe Bankham can speak to that here.
Yeah. So for the training, we are having training, but we're doing things a little bit differently with training. So it won't be through the CFP. We're doing some curated classes, but we are still looking for those. So if anyone's interested in presenting a training, come talk to me or come talk to Matt Pardo. I don't know if I didn't see him here today, but just come talk to me after or put him in my direction. And then the training will be posted once we have those courses. So we're hoping probably the midsummer is when the training classes themselves will be posted for signups.
Thank you, Bankham. Upcoming events. I know that Matt Pardo also is looking in some other training opportunities, and I'm not sure if he has anything able to mention. Of course, he's not here right now, but stay tuned for that. The Austin Security Professionals Happy Hour, the next one is going to be June 8th, and it's going to be at Sherlock Baker Street Pub. And just listing a few of the upcoming local events. And I believe ISSA has a pretty good calendar that keeps all of that up to date if you're interested in seeing what all's going on. And I'd like to take the time now for any job opportunities, if someone's actually hiring, if they want to have any announcements. Okay. And now presenting, we have a three-part presentation, and so I'd like to introduce first Gabriel Cornyn.
see, yeah. There wasn't any other way to do it otherwise. So hi, thanks everyone for coming out. We're excited for our first together presentation. We never really settled on a title slide, so it's just called 3 web vulnerabilities at the moment. We're not exactly sure where the annoying web vulnerabilities component came from. I am Gabriel Cornyn, and I'm going to be talking about HTTP request smuggling today. Ben and Jacob, if you want to say that. And that was about it for that. Yeah. So just getting right into it. Yeah, I'm going to be covering request smuggling, and I'm going to start off with a sort of a timeline because there's a family of related issues. Response splitting, request smuggling, response smuggling, and request splitting. Basically, every permutation of requests and responses, and splitting and smuggling, you can kind of throw a hat at. The person to sort of notice here is Amit Klein. He was responsible for a lot of the white papers that came out on this topic, this family of topics. The one that I'm going to be talking about today, he kind of worked with a bunch of other folks to write the white paper. And most of what's presented today is going to be coming from the white paper, but there's also some references to OWASP. Does this only cover online, or is there also speakers? Yeah, okay. So yeah, the family of issues, mostly done by Amit Klein. Yeah, thank you. Amit Klein, as well as for my topic, a couple other folks. And most of the information for today is going to be coming from the white paper. And then, so let's just get into it. So the way that you're accomplishing this is you compose, as a malicious actor, a series of requests in order to bypass an intermediary device, or the inspection that an intermediary device would typically be giving a request. So the way that this is accomplished is using non-RFC compliant behavior within a single request in order to cause 2 different agents that are inspecting the request chain to see basically 2 different versions of reality. You can accomplish a couple different things with this, and I'll be going into each of these in more detail in the following slide. But the main entry, or the main item that we're going to be focusing on in this presentation is the poisoning page entries on a caching web proxy. But another really interesting one is bypassing controls to deliver uninspected content to the web server. So basically, if you have a wireless web application firewall, you can convince it that your request is legitimate. You can deliver something that's your actual content to the web server and do standard exploitations from the 90s that should not be possible with sort of more modern inspection. So per the white paper and from Amit, basically, whenever there are multiple agents in line in the request chain, and they're all, and this is essential, they're all parsing the request, there's a good chance that at some point HRS or HTTP request smuggling is feasible. It could be a proxy, and that doesn't have to be a caching proxy. It can just be a proxy, firewall, IPS. As long as it's parsing the request in any way, it has to make assumptions about what the request looks like based on what it's seen and how it's programmed to respond. So just restated, discrepancies in the way HTTP data is parsed can result in the perceived state of a request differing between multiple entities, or agents, really. So this is sort of a cut-down version of the classic example for request smuggling. You'll notice the highlighted content links 0 and 28 here. And so this is essentially the request, one single request, despite the fact that it looks like maybe 2 requests or more, depending on how closely you're looking at it. It's one transmitted request from a client or from a malicious actor. So basically, the point here is that the content link header occurs twice, and there's no appropriate way of handling that. One implementation might choose the first, one implementation might choose the last. So whatever happens first is law, or whatever happens most recently is law, depending on how they determine to accept that or how they sort of store that internally. I have a coworker at Rapid7 who says, from his background with sort of network protocols, be strict with what you send and be tolerant with what you receive. So if you're sending this and you're relying on the good graces of the devices that are actually parsing the request, then they may see different versions of reality, essentially. So we'll get into this a little bit more in more advanced example in a minute. This is a more fully formed version of the classic example. And this is actually going to be what the client, what the malicious actor is actually sending. This is all essentially one request, despite it looking like it has a GET for a poison page or a second GET on line 11 for a target for poisoning. And we're going to walk through this, and that's going to be basically going to show you how this is kind of working. So the client sends this data, and we know, I'll back up for a moment. The issue with request smuggling, or the essential requirement for request smuggling, are that you need to know what the behavior of the web server you're targeting and the intermediary device that you're targeting, how they operate. And if there's a differentiation that you can give on how they parse certain requests, then you can leverage that differentiation to do your malicious actions. So in this case, we're going to be poisoning a caching web proxy with basically our choice of page. So the caching proxy in this case uses the final content link header of 52. And so you see a post, you see content link 52, you read into the second request, well, the body rather of the post request, 52 bytes, and that gets you through this junk header, colon space, no carriage return line feed. It then sees a second complete request for target for poisoning. So from the point of view of the proxy, the caching proxy, it sees target for poisoning as the second request that's being sent by the client. It trusts this to be true, and it passes on the first request, completes the circuit, then passes on the second request to the web server. And then from the point of view of the web server, it sees the post request, it chooses the first content link header, it sees that there's no data in the post request, it's just a naked post request. It then sees a second request for poison.html. When the response from the web server comes back through the proxy to the client, the caching proxy will cache poison.html, the content of poison.html, against the request for target for poisoning. Now, the interesting thing, you've done something interesting, it's sort of weird. When an innocent client comes along and requests target for poisoning, and that could be anything, index.html, you've redirected it theoretically to like a 4 page. So you've kind of arbitrarily caused the web server denial of service itself. So by doing this, you've evaded the caching web proxy's standard means of sort of inspecting the content and responding to it intelligently, and you kind of cause this arbitrary issue that's under the attacker's control. What's interesting about this is that it's only a partial, the attacker only has partial control, because in this instance, you are not able to upload your own content. You're only using what's sort of available on the page already. If the malicious actor is able to upload their own content, they could redirect legitimate clients to content of their choice and cause much worse, sort of secondary effects. Yes. So the white paper goes into a lot more detail as to all the different things that you can do with this attack, and basically references the original HTTP 1.1 spec. The white paper, I would recommend checking it out. It has some interesting sort of things to say about how to mitigate this issue, but none of them are super strong recommendations. It sort of includes terminating requests after terminating request chains after a single request, so that you're basically back to sort of 90s era web where you're having to set up a connection for every item, for every resource that you want to request. It's not very practical. And then other things such as basically to say for this specific instance where you're just dealing with caching web proxies, set everything on your web server to deny the ability to cache any of the content. So also not very amazing, but we can go into more detail on the next talk. And yeah, that is me. Ben?
Can y'all hear me? Is that coming through? Especially over there in the back? Yeah, cool. All right. I tend to speak kind of quietly, so I'll try my best to project. Okay, so as Gabriel said, I'm going to talk about HTTP response splitting. There's a lot of similarities in what he just talked about and response splitting. And one of the main points is that basically the walkthrough I'm going to give is also cache poisoning. So these are basically two different ways that you can do cache poisoning. But there are other attacks that you can use response splitting to accomplish, which I'll get to in a second. So that should be a GIF. Anyway, whatever. He does the split, and that's response splitting. So that didn't go very well. Okay, so another name for response splitting is CRLF injection attack. And the reason for that is because the attack relies on the acceptance of a carriage return and a line feed, or CRLF. You can see up there the different ways that these can be represented. I'm going to stick with the URL encoded one at the bottom, the %0D, %0A, just because it's in most of the examples that I was going through, and it made the most sense to kind of stick with that. So. And what I kind of touched on just a second ago is that this attack is really a means to an end. It's used to perform other attacks, cache poisoning, cross-site scripting, some other things that I'll go into a little bit later. And in this attack, they're going to be, well, in the material I was reading, they kept saying there's at least 3 parties in an attack. It seems to me that there's really 4 or more. So I'll just go through that real quick. There's going to be a malicious attacker or pen tester, depending on what's happening. There's going to be a vulnerable web server on the other side. And in between there will be a proxy or cache server most of the time. And in doing this attack, your target is the proxy or proxy or cache server, but your end result is to affect users. So that would be the 4th component. So how, why, and where? How this happens is a malicious attacker, or really anybody, is able to pass information to the server that is then returned in a header, which is usually, as you can see at the bottom, a location header or a set cookie. So in the malicious example, the attacker is sending a single response, and that response, by the way it's crafted, is going to be split into 2 responses, which is read by the web server. Sorry, it's read by the web server as 2 responses, and then that's passed to the cache server or proxy server. In a roundabout way, I got to that second point, which is the user input is embedded into the response headers. Okay, so I'm going to go kind of back. This is really basic information. You'll probably all know this, but I just want to go through this so we can build kind of what is going to happen in the future and just the key parts of what's actually happening. So if we send a GET request, your normal HTTP response is going to have two parts. You're going to have your message headers. Each one of those is going to be separated by a single CRLF. And then you're going to have a CRLF pair that will split the headers and the message body. And that's per the HTTP standard, which is RFC 2615. And then still in the basics, this is just what our basic request. This happens to be to rapid7.com. And then the response, which is showing both the message headers and message body, and notes in between where it says snip right below that. So there's your CRLF pair there splitting this. And so the cache is going to, the cache server is going to come into play as we're talking about the vulnerability and how it works. So I just want to go over kind of a basic how the cache is like processing information. So user is going to send a request. Request goes through the cache server, goes to the web server. Web server responds with, in this example, index.html, goes back to the cache server, and that gets served back up to the user, or the page gets served to the user. In the subsequent responses, the user is going to send, this is probably a different user, or it's the user later, is going to send a request for that same page, and then the cache server is just going to respond instead of passing it back to the web server. So I'm going to go through two different examples. So this one's the non-malicious example, and then we'll have the malicious example. And in both situations, we're basically looking at an application that lets the user pick an interface type. So it's either normal or it's advanced. In this request specific example, we're selecting advanced. And the important part here of note is that the user selected advanced, and the server is embedded that into the location header. And that is what, basically, it's allowing user input, which is the problem. So now we'll go into the malicious example. So this is hard to read, but you can see that interface is still equal to advanced, so we're still submitting that. But then we're also tacking on a whole bunch of other stuff that's going to cause what we want to happen. So again, this is user or attacker controlled and submitted. And these are the CRLFs that are important. And the reason they're important is they kind of, oops, sorry about that. What did I do? Dang it. Sorry. Going back. There we go. So the reason they're important is that they're splitting up responses and requests, well, their requests and responses. So this first CRLF pair is going to split the web server, basically the expected web server response, and then the second response is going to be the attacker-controlled response. So the next CRLF is going to split the attacker response headers and then the body. So you'll have a full response in that. And that's nothing. Okay, so I'm also going to go through this line by line so we can kind of see what's going on. So line 1 is the submitted content. And so there's a few things happening here. But basically, we're submitting a content length of 0. And then on top of that, the CRLF pair. So this is telling the servers that basically this is the end of the request. So this part is going to be the response headers that are injected in the attacker injected response headers. We have another CRLF pair that's going to split the headers and the body, and then we have a body. In this case, this will make more sense later probably, but we have a responsive system down. And then this is just a little clearer what's actually happening. So something to note here, I guess, is that in the expected response, So there's the ignored data at the end of this. And so in a normal response without injection, the normal expected response from the web server is going to include some of this other data. But the way we're crafting it, it's actually getting ignored because we're saying, hey, stop. Here, the content length of 35 in the green section, and then the body itself will just tell the server that that's the end, and so everything else is ignored. Okay, so how does this really work? As far as cache poisoning goes, the attacker is going to send a single request, gets split into two responses. And then the attacker will also send a second request for index.html as an example. So in this situation, the web cache is going to match the first request with the first response that the malicious, first request to the regular web server response. And then the second response that comes through will be sitting at the cache, and then the attacker sends the second request, and that gets matched, and that gets served back. So basically, the cache server is waiting for that request to come through because it's got an extra response that it doesn't know what to do with. And just diagram it out so it's a little clearer, hopefully. So attacker sends request A. Request A has the request and the injected response. So it gets passed from the cache server to the web server. And here's where it gets split, and it gets sent to the cache server. So response A is going to be the normal web server response. Response A1. Response A2 is going to be the response controlled by the attacker. And so the normal response gets passed back to the attacker. And you can see A2 is just sitting there. What's it doing? Just waiting for requests to match with the response. So the attacker sends a second request, and that gets matched, and it goes back to the attacker. So what that means is now the cache server is poisoned, and it thinks that the response to index.html is what the attacker sent, which in the case before was system down. So we have a user, sends a request for index.html, and gets the attacker's response. So basically, you know, they think this is the application is down when it's not. So there's one piece of this that it's a little more into the detail than I really want to go, but I just want to touch on that real briefly. So what happens if the resource is already cached? So there's a couple of different things you need to do in this situation, and one is to send an initial request, and it's going to contain the cache control or pragma header with the no cache. So that's going to invalidate the cache for the resource. And then in the injected response, you also have to put this last modified header and set it to a future date, so that will actually be cached. So these are some of the vulnerabilities that you can use response splitting to accomplish. We talked about cache poisoning. Cross-site scripting is a big one. These last two, cross-user defacement and page hijacking, they're a little bit more targeted to specific users. So the top two, cross-site scripting can be as well. But so what was interesting as I was going through this is page hijacking. Basically, you can convince in the same process, you're sending the two requests, or two responses, I should say. You're confusing the cache server when there's another user involved, and you can actually have the cache server return the user's, say, login page information, the response to that, and then send them whatever you want. So I'll show you this really simple example of what that looks like. Just kidding. I'm not going to go through this, but the point is that the bad guy gets the normal user information, and the normal user information, or normal user gets the bad guy's whatever he wants. So I was in this research I was doing. So I'll just say this: there are a lot of bigger websites, companies that are vulnerable to this type of thing, the response splitting. Google, Reddit is my example here. Cisco ASA, Twitter. So lots of ones out there. The proof of concepts are not incomplete. So this is just kind of a brief touching on what happened with Reddit, for example. So can I go into that? So here's a request that's basically sending a cross-site scripting script. And so you can see the kind of thing to point out here is that there are two location headers. And that's because this specific request injected a location of JavaScript. And basically what that is doing is it's confusing the server, and it's in some complicated manner. It's actually just telling the browser, hey, look, read this body. And so in doing so, I'll skip through this, sorry. In doing so, you get the kind of classic pop-up. It's not pop-up 1, but I read it either way. So anyway, so how do we fix response splitting? Standardization. So just a common thing. It's a common resolution to a lot of vulnerabilities. Just don't take user input. Make sure everything's sanitized and use server-side validation. And as Gabriel mentioned, one of the really good resources for this topic is Emmett Klein's white paper. And then here's a couple other things that I thought were pretty interesting. And this last one actually is where I got the proof of concept for Reddit. So if you want a little more detail on that, check that out. And that's it.
So cross-origin resource sharing, that's my topic. The overview for what I'm going to talk about. I'm going to go into some of the course headers. I'm not going to go over all of them. There's plenty on the server side that are used for different situations. Then I'm going to talk about the limitations of the headers that are included in this talk and how those limitations set up these misconfigurations, because people are trying to work around the limitations, but those could address or basically provide additional situations you have to deal with if not done correctly. And then finally, mitigations. But before I jump into the CORS topic, why does CORS exist? So I'm pretty sure most of you know of the same origin policy. It's a very important policy that protects the internet. It's why you can't just go to one malicious site and then all of a sudden start making requests and retrieve like your bank account information or information from other social media sites. Because when requests are made, if you're logged into a site, the browser will automatically include a cookie. And basically what the same origin policy does is it prevents a malicious site from reading the responses. So here's kind of an example of that. So host1.com, host2.com. So you're a client, you use your browser, you go to host1.com, it loads some JavaScript in your browser that makes an AJAX request. So maybe host2 is like a bank or something else that an attacker would consider to be of value. The response comes back, and so the browser will check, are the origins the same? And the origins determined by the protocol in use, the host name, and also the port. So it sees that these are different, and it blocks the JavaScript from reading that response. So that's very important since cookies are automatically added by browsers. This protection needs to be in place, which is really good, but it's highly restrictive as well. So say you're a business, host1 is a company you own, host2 is a company you're partnered with in some way, and you want to share information. You want to be able to access information on one site and have the other host maybe displayed in a different manner, or they've done some customizations that you're okay with. So in those cases, you say, hey, this is too restrictive for my business purposes, and there's other situations where needing to share content across sites comes up. So that's kind of where CORS comes into place. It allows the server, so host 2, in this example, to set a access control policy that specifies which origins can access its content that you need to be authenticated to see. So it could tell the browser, hey, if it's coming from this origin, allow it to access this content. I'm okay with it. Don't block it. So the way this is actually done is with headers. So on the requesting side, there's the origin header. The browser will automatically place this in request. So I have tried in JavaScript to set this header, but the browser would just be like, no, we're going to go with what I say, and it would just override it, so it doesn't let you set it. On the server side, the response headers, access control, allow origin, that's used to tell the browser who can access this content, and access control allow credentials is whether the user has to be authenticated to access that particular resource or not. There's other response headers, as I mentioned, but these are the two primary focus for this talk. So going into an example, how we did the same origin policy, this is going to be with CORS. So again, host1 and host2.com. You go to host1.com and makes a AJAX request, but the origin header is provided by the browser. It automatically inserts it. You don't have to worry about that. So the host2.com has to determine whether or not it's going to trust host1.com. And it does that by setting the allow origin header. So in this case, it says, yes, HTTPS www.host1.com is, I'm going to trust it, and I'm going to trust it with credentials. So everything's all well and good. The browser allows the JavaScript to read the response. So if it wants to do additional manipulation, log it however it wants, or display it differently, it has access to that data. It's not blocked. So a blocked example would be kind of same setup, but this time the origin, it's saying, I want API host2.com, not host1.com. So the browser sees that the origin is different. It will go through and block that request. So host1.com can't read that. So that's kind of how it works, how you could set up headers in order to give a policy, and the browser will enforce that. So it's really a communication between the server and the browser. The server will say, these are the conditions. I will allow it to be valid, and the browser has to parse that information and then enforce it. So it's a communication between both. So allowed values for these headers, the allow origin has a wildcard. It also has where you can set the host name, as we saw, api.host2.com and host1.com, and then no value. For the allow credentials, it's kind of just true and false. So whether you have to have a user that's logged in to access the resource, or it's publicly available, depending on the allow origin header. So with these values, there are limitations. With the wildcard, that cannot be used with allow credentials true. So what that does is it prevents you from basically destroying the same origin policy completely. You can't just say every server out there on the internet could make a request to my site with credentials and I'll accept it. So if a browser sees the wildcard with the allow credentials true, it basically just ignores the allow credentials true, and it'll treat it as an unauthenticated request. So that's kind of good. It prevents you from doing really bad things if you don't know exactly what you're doing. But for limitations of the wildcard, you can't really use it in a string. So you can't say, I'm going to trust HTTPS star.host2.com. That's not possible. It's just standalone by itself. If you try to use it as part of a string, the browser will basically complain and not let you do that. For host name, so it's just singular. You can't provide a list of, say, I trust API host2.com or demo.host2.com. So you can't list out multiple things. So you're kind of restricted to just having one host name there. So that's kind of really prohibitive if you want to just trust all your subdomains, or you have multiple people that you're doing business with and you want to provide them all with a certain level of access to your resources. And null is special. So with null, there's kind of an assumption that if there's a null origin, then it's coming from the local host. So you get in a situation where there's kind of an assumption that if it's null, then it will be coming from the local host, but that's not always the case. There's specific things that you could do with iframes and setting a sandbox attribute that will provide a null origin. There's a talk that was at AppSec USA by James Kettle that he kind of goes into more detail about that. It's really interesting. So with all these limitations in place, how do people try to get around it if they do want to trust multiple different sites? So a way to get around that is with dynamic origin generation. So basically, when you see a request come into your server, you have to decide on the fly whether or not you're going to trust that origin. So that provides you a little bit more flexibility. You don't have to say, I'm going to trust only one host. You don't have to say, I'm going to trust everyone, but I'm not going to let them use credentials. You could do more things. But then you get into a case of where this could be a misconfiguration if you don't do it right. So two of the ways that I've kind of, when I was reading about it, that people mention is just return the origin that is in the request, which is really bad because then you get to where basically you have a wildcard with allow credentials true. So the thing CORS is trying to prevent you from doing in the spec is now you're basically allowing that to happen. The other option is just more thorough logic to try to validate the origins, which ones you're going to allow and which ones you're not. So kind of what your headers are going to be based on what you see coming in. So kind of an example of that, abbreviation of allow, just because I don't want to say it all the time. So you have evilsite.com. This is the first one where you kind of just return the origin that you see, and host2. So host2 sees that comes in, and then it automatically says, oh, yeah, sure, whatever. I'll trust that user. So then think about every host out there on the internet. If they find out that you kind of have this going on, any site could basically make requests on a user's behalf, and they could retrieve resources that you need to be authenticated to have. So this one has an extra header in there, the very origin. So if you're doing dynamic content generation, that's important to instruct caching servers to not use the response that they see for every different host name. So if you're sending out content depending on the host name, you don't want to have different site A see content that was supposed to be for site B. So that's kind of there to instruct caching servers, hey, don't store this. If you see another request comes in by a different host name, make sure you change it. So the other example of, well, dynamic content generation, origin generation, is let's say host2.com figures out they misconfigured their server. They're returning the origin that was in the request all the time, and they don't want to do that. So one thing they could try is say, okay, let's only allow from host2.com. They verify that that's at the end of the origin string, and if it is, then they're all good. But issues could go wrong here as well, or issues could occur here as well. So then you have host2.com sitting out there. They made their code to try to validate the origin based off of, hey, let's just see if host2.com is at the end. But then you get where a malicious actor could just register a site that, hey, I'm evil-host2.com. So although they tried to prevent different sites out there from accessing their protected resources based on the origin, if you don't do it correctly, then you end up in a similar situation where someone could still get around your validation mechanism. So in this case, you send a request, the origin header's there, host2.com says, hey, it's host2.com at the end of it. All right, I'll accept that as valid and put you into the allow origin. So just kind of a note here that if you are doing dynamic origin generation and you're setting those headers based on what you see, make sure you validate it and check for these cases of, if you're just looking at the end, well, make sure you actually check the entire string. Because a similar thing can happen if all you're doing is saying, well, let me check https //www.host2.com. So if you're only checking for that, but you're not making sure that's the entire string, then somebody could just say, okay, we're going to be https //www.host2.com.evil.com. So you have to verify that the entire string of the origin is what you're looking for, or issues could occur. So mitigations, it's not really mitigation since it's a misconfiguration issue that can happen. It's more things to consider if you're implementing cores. So first of all, if you know you want to trust a single site, then having a static hostname would be the best. So you don't get into all these weird issues of dynamically generating which origin you're going to trust. And if you are doing some dynamic logic, make sure you validate that. A way you could do this easily is with curl. If you use curl, you could set headers. So you could just say origin equals evil.com and see if that's returned. Or since you know the name of your site, try to get around or try those corner cases of maybe I just add something onto the end. Does it return it? Or if I add on to the beginning, does it return it? So there's also, do you really even need cores? Are you intending to share content with other people? Do you want to give other people access? If not, then maybe just disable it completely. So as I mentioned null, the null value before, if a server does have configuration for allow origin and you don't put anything, sometimes it will just assume it's null. So when you're doing, even though you think it's disabled, it might actually be enabled. So run some checks with curl and see if it's enabled or not. So just add the origin header. You can do that with curl. Everything will be good, hopefully. So here's some references. I highly recommend the talk by James Kettle. He goes into more detail about if you're not using credentials, so if it's set to false, other issues that could arise. That basically gives a website access to the internal network to try to make requests on your behalf, as well as goes into more information about the null and how that's used and how you could kind of get a server to have that origin and make requests. So that one's a great resource. Just kind of wanted to throw this out there. If you need to provide a proof of concept, one of my coworkers did make a Python HTTP server that you spin up, and you could give it a URL of the resource that basically has the course misconfiguration. And then you'll spin up a server and open it up in your browser, and it'll make the request on your behalf and kind of dump that data. Just kind of wanted to mention that if you do want to have a proof of concept. It's on GitHub, so it's open source. And thanks. Yeah.
So we have a little bit more time. So if you have any questions for Jacob, Ben, or Gabriel, anybody have any questions?
with all these microservices where the general what's advocated is using some form of HTTPS just to get at a piece of data. Are any of the controls in there, or are you just in the Wild West?
So if the requests are going through a web browser, then it's the web browser that actually enforces those controls. So, I mean, if you're going through a web browser, yes, the controls are there. But so you mentioned like HTTPS, and all my examples were HTTPS. So you also have to think about whether you want to trust HTTP sites, because those sites could be vulnerable to man-in-the-middle traffic if an attacker is on the same network. So they could say you're trying to go to http.google.com. So if you try to go to HTTP and somebody's man-in-the-middling that traffic, then you could provide some JavaScript, and it seems like it's coming from Google. The browser will put the origin as Google. So there are different cases where things come up like that. But if the web services are going over provided through a web browser kind of interface on the back end trying to handle it, then the browser does automatically add these headers and try to enforce these policies.
But as I understand it, the beginning of the whole interchange is that host one.
Yes, so
and I don't think there is. If someone here knows how these microservices subsystems work.
So CORS is when you're doing microservices, you're kind of communicating on server backends usually, not all the time. And CORS is kind of a way to do that, but across the internet. So it's assuming you are using a web browser, and it's kind of a replacement for hiding all these types of things happening on the server backend, if that makes sense.
Anybody else have any questions? Okay, well, we'll get finished here early, so thank you very much, and we'll see you next month.